Okay, let's continue on with our discussion of reacting systems. So last time we talked about the reaction mechanism for a particular chemical reaction. That's the recipe or relationship that relates reactant species to product species. Does not include inert material, inert species, or components. And then we did an example to find a reaction based on a reaction mechanism. Today we're going to expand a little bit more. And then we also talked about air-fuel ratios, both on a per mole and a per unit mass basis. So that's what we did last time. Today we're going to talk about theoretical air, or theoretic air, lambda. We're going to talk about stoichiometric reactions. What is a stoichiometric reaction? And then we're going to link that to the theoretic air lambda. We're going to talk about excess air, so when we add more air than we need in a reaction, or we have less air than we need in a reaction. Talk about rich, lean versus stoichiometric combustion. And then we'll do an example involving use of theoretic air or excess air. Okay, that's our plan for today. Okay, so I want to define a term here, and the term is stoichiometric combustion. So what is stoichiometric reaction? Combustion reaction is all the same. So what's a stoichiometric reaction? A stoichiometric reaction is a reaction where there is just the right proportion of oxidizer and fuel, or air and fuel. So a ratio of air and fuel such that no fuel or oxidizer is present in products of combustion. Okay, so we're starting off with just the right amount of air and fuel such that there is no excess oxygen in the product. There's no oxygen left over in the products. There's no fuel left over in the products. We're assuming complete combustion. So we're assuming no fuel in the products, no oxygen in the products, complete combustion, just the right amount of air. So that's referred to as a stoichiometric reaction. Basically, it's the reaction mechanism including the nitrogen component. So if you write your reaction mechanism, which is completely balanced, and you write the N2 in there as well, then you'll have a stoichiometric reaction. So the example that we did last time was a stoichiometric reaction. As you recall, the combustion of butane in air had no butane in the exhaust or the products, no oxygen in the products. So that was technically a stoichiometric reaction. The example we just did was a stoichiometric reaction. Now, in most internal combustion, in most devices involving combustion, you want for maximum efficiency. So typically for maximum efficiency, you want to have a mixture of fuel and air, or fuel and oxidizer. So to maximize performance. To maximize performance, you basically want or nearly a stoichiometric mixture, a stoichiometric reaction with a stoichiometric mixture of air and fuel, or oxidizer and fuel. So you want a stoichiometric reaction. So just the right amount of fuel, just the right amount of oxygen, minimizes emissions, produces the most heat release, And your internal combustion engine produces the most power, the best emissions, best fuel economy. You want to be near a stoichiometric reaction, So to maximize efficiency, you really want to be operating at an air-fuel ratio. An air-fuel ratio, stoichiometric. You want to be operating at a stoichiometric air-fuel ratio to maximize to maximize performance. That's basically what you want. Now, sometimes, depending on conditions or depending on constraints or specific desirables, you may want to deviate away from stoichiometric for whatever reason. So in that case, we define what's called theoretic air. So theoretic air. Let me make sure I got the terminology right. I always forget this thing. Let's see here. Theoretic air, yes. So we define a quantity called theoretic air, lambda, which is the ratio of the actual air-fuel ratio. It could be on a per mole basis. It could be on a per kilogram basis. The ratio of the air-fuel ratio, the actual air-fuel ratio to the stoichiometric. Air-fuel ratio. It doesn't matter whether it's on a per mole basis or on a per mass basis. So this lambda, theoretic air, lets us keep track of how much air we're adding to the fuel to burn and produce the heat release and the products of combustion. So what are some various values that lambda can take? So lambda can take many different values. First of all, lambda can equal 1. So if lambda equal 1, that means the air-fuel ratio is the stoichiometric air-fuel ratio. So if lambda equals 1, that means stoichiometric combustion. So we have a stoichiometric mixture, which is then burned. Just the right amount of fuel, just the right amount of air for complete combustion, no more, no less. Now, lambda can be greater than 1, so we can be greater than 1 as well. We can be equal to 1 or greater than 1. If lambda is greater than 1, that means the actual air-fuel ratio is greater than the stoichiometric air-fuel ratio. That means we have excess air. We have more air than fuel, more air than we need for the given amount of fuel that we're trying to burn. So more air than fuel. So this means excess air, and that's called lean combustion or a lean mixture. Lean mixture. Excess air, too much air, excess air, or more air than we need. It's called a lean mixture. Lambda can be less than 1. That means the air-fuel ratio is less than the stoichiometric air-fuel ratio. That means we have more fuel than we need and not enough air. So this is excess fuel. And this is called rich mixture. So we have a rich mixture of air and fuel. A little bit more, too much fuel. Excess fuel. Lean, too much air. Lean mixture, too much air. Rich mixture, too much fuel, or more fuel than we need, more air than we need. If you want a little history here, in the old days when automobiles, before we had emission control, before we had catalytic converters, before we had emission control requirements or emission standards, typically to maximize power and fuel economy, automobile engines, the gasoline engine, tended to run ever so slightly rich, just a little bit more fuel than they needed. And that resulted in fairly high combustion temperatures, very high peak temperature, higher peak temperatures in the combustion chamber during the cycle. Slightly better fuel economy, more power, better performance and acceleration. The cost was, of course, a reduction in the emissions, and an increase in the emissions or a reduction in performance in terms of emissions. So typically having a rich mixture means that you have more carbon monoxide and hydrocarbon in the exhaust, and that's not so good when it comes to a clean environment, okay? And then when the early emission control stuff started coming in before catalytic converters, some manufacturers try to go to a slightly lean mixture, provide too much air. The idea was to give the fuel as much air and then some as it needed to oxidize, and that would minimize emissions. Well, there are a lot of performance problems involving lean mixtures. Acceleration's poor, engines tend to overheat. The mixture can burn so slowly that when the exhaust valve opens, you can have actual flame coming out of the exhaust port. The air-fuel mixture can still be reacting, and that tends to overheat the engine, overheat the valve train. So today, with catalytic converters, electronic fuel injection, the idea is to achieve and approach as much as possible just plain old stoichiometric combustion. Not too much, not too little. Some manufacturers are still working with lean combustion, but most of them are stoichiometric. There's still some research on lean combustion engines, and they're making some progress, but they're not there yet. So that's some of the history on theoretic air and the values that it takes, lean, rich, and stoichiometric combustion, okay? Let's do an example. Let's do an example here. Let's do an example. So let's return to the example that we had last time with a couple of modifications. So last time we had combustion of butane with air. Well, now, and that was stoichiometric combustion. If you look back at our example, you'll find that N dot O2 at the exit and N dot C4H10, the fuel, the butane is also zero. Everything was converted into CO2 and H2O, and of course there's a nitrogen that doesn't participate in the reaction. So that was a stoichiometric reaction, the example that we did, the first example that we did involving determining the reaction was stoichiometric. We're going to build off of that. We're going to take our results from the previous example, and we're going to recalculate mass flow rates and therefore the reaction for 50% excess air. We're going to set lambda equal to 1.5, 50% excess air. In addition to that, combustion is not complete. Not all the fuel is burned. This is more realistic. In most realistic combustion situations, not all the fuel is burned for various reasons. So in this case, N dot for the fuel, N dot C4H10 at the outlet in the products is equal to 10% of the inlet flow for the fuel. In other words, 90% of the fuel is burned, 10% isn't. So I'm going to write in parentheses, i.e. 90% of fuel is actually burned, leaving the remaining 10% unburned in the products of combustion. Okay? Okay, so let me put the diagram or the schematic in here. So here's our schematic. So here's our inlet port or our inlet locale, our reactant side, and our product side. Here's the flame. So let's see here. Let's look at some quantities from last time. From last time, the N dot for the air. The N dot for the air from last time, so N dot air from last time, if you look back at your results, it was 123.8 kilomoles per second. So N dot air, stoichiometric. That's from the last example, was 123.8 kilomoles per second. 123.8 kilomoles per second, okay? So the new flow rate is 50% more than that. So N dot air A is equal to lambda N dot air A, and that's stoichiometric. So that's 1.5, 50% more, 123.8 kilomoles per second. And we get a airflow rate in this new excess lean combustion. More air than fuel than we need, so it's lean combustion of 185.7 kilomoles per second. 185.7 kilomoles per second. So we have 185.7 kilomoles per second. Okay, so that's our new airflow. That's our new airflow. I'll recall N dot for the fuel, N dot for the C4H10 at the inlet was 4 kilomoles per second. Okay, so remember that. Again, we're told that only 90% of the fuel is burned, leaving a remainder of 10%. So at the outlet, N dot C4H10 on the product side, there's a B there, is going to be 10%. 90% burned, leaving 10% remaining. So 10% of 4 kilomoles is 0.4 kilomoles per second. Only 10% remains unburned in the products, okay? So what are we supposed to find? We're supposed to find the air-fuel ratio, both on a per mole and a per mass basis. We're supposed to find N dot air. Well, actually, we just calculated that, so fine. And then we're going to find the reaction. Okay, so let's get this going here. So lambda, air-fuel ratio over air-fuel ratio stoichiometric. So let's remember that. So analysis. So lambda equals air-fuel ratio over air-fuel ratio. Could be on a per mole basis, could be on a per kilogram basis. I'm not going to write stoichiometric, I'll just write stoich. I'm tired of writing stoichiometric. Or air-fuel ratio over air-fuel ratio stoichiometric. Okay, per mole, per mass basis, same thing. That's the definition of theoretic air, or lambda, the ratio of the two. Okay, so that means the air-fuel ratio per unit mole on a per mole basis is lambda air-fuel ratio for the stoichiometric reaction. And we got from last time on the previous example, which was a stoichiometric reaction, we got that the air-fuel ratio on a per mole basis was 31 kilomoles of air per kilogram fuel, per kilomole fuel. So 1.5 times 31 kilomoles of air per kilomole of fuel. And so that gets me about 45, just about 45. 46.5, 46.5 kilomoles air over kilomole fuel. Okay. So air-fuel ratio on a per unit mole basis, 46.5 kilomoles air per kilomole fuel. Okay. Same thing for the air-fuel ratio on a per mass basis. So that's air-fuel ratio is equal to lambda times the stoichiometric air-fuel ratio. We already calculated that in the previous problem. The stoichiometric air-fuel ratio on a per unit mass basis, I got it here somewhere. Yes, 15.4 kilograms of air per kilogram of fuel. 15.4. Hold on a second. Yeah, 15.4. 15.4. 15.4 times 1.5. I guess I'll do this in the right order. 1.5, 15.4, and I get whoops. There we go. 1.5 times 15.4, 23.1. And that'll have units of kilograms of air per kilogram of fuel. So the air-fuel ratio is equal to 23.4 kilograms of air per kilogram of fuel. Okay, so now we have the air-fuel ratios. Now we have the air-fuel ratios. Okay. Now we already calculated the airflow rate. It's simply lambda times the stoichiometric airflow rate. So it's going to be 50% higher. So we've already calculated n dot air. So that's all done. That's all done. Check. Okay. Now let's calculate the reaction. Let's go through and do the reaction here. Let's go through and do the reaction. So I'm going to erase this. We don't need it anymore. And we're going to put up that big table again so that we can find the mass, the mole flow rates, and therefore the reaction. The reaction mechanism is the same. It's still oxidation of butane, combustion of butane in oxygen. So nothing has changed there. Hopefully we'll have enough room here. So we got the component, stoichiometric coefficient, n dot I, the component flow rate at the inlet on the reaction side. And then we have n dot I, the mole flow rate on the product side, is equal to the mole flow rate on the reactant side plus the stoichiometric coefficient times the reaction coordinate, epsilon. Our flow rates are all different now, so the reaction coordinate is going to be different than when we did the previous example. You'll see this. So let's list our chemical components here. So we have the C4H10, we have the O2, we have the CO2, we have the H2O, and we have the N2. The stoichiometric coefficients from last time were -1, -6.5. What was it? 4? Yes. 5 and 0. Nitrogen is inert, so its stoichiometric coefficient is 0. 0. Okay. Okay, so let's write what we know here. N dot fuel at the inlet. So n dot C4H10 at the reactant or the inlet side is 4 kilomoles per second. Okay, that sounds good. Got that written right there as part of the problem statement. Oh, O2, what's the flow rate of O2? Well, N dot O2 at the inlet is going to be equal to the mole fraction, 0.21 times, running out of space here. I'll tell you what, I'm going to move this just a little bit. It's going to be equal to the mole fraction, 0.21 of the air. Okay, 0.21 of the air. There's no inlet flow of CO2 on the reactant side, no inlet, no reactant flow for CO2, so that's 0. Same thing for the H2O. No inlet H2O on the reactant side. And then N dot for N2 on the reactant side is equal to the mole fraction of nitrogen times N dot air. 79% nitrogen, 21% oxygen, O2. So oxygen mole flow rate and nitrogen mole flow rate are their mole fractions in the air mixture times N dot air, okay? And we'll get some numerical answers here hopefully pretty soon. Okay, let's proceed now. Let's calculate, let's go through and start working on the product composition. So let's see here. The outlet flow rate for the fuel is going to be equal to N dot C4 H10 at the inlet plus the stoichiometric coefficient, -1, times the reaction coordinate. And by the way, plugging in 4 kilomoles per second minus the reaction coordinate. And the outflow mole flow rate, the outflow rate of fuel, it's unburned fuel, is 0.4 kilomoles per second. 0.4 kilomoles per second. So this is, I guess I'll write it here, N dot C4 H10 at the outlet. Okay, there we go. And the outlet mole flow rate is 0.4 kilomoles per second. Well, that implies solving for epsilon. The reaction coordinate epsilon is 3.6 kilomoles per second. So epsilon is 3.6 kilomoles per second to give us that outlet flow, non-zero outlet flow of unburned fuel. Okay? Let's do the O2. N dot O2 at the outlet is equal to N dot O2 at the inlet, product reactant, plus reaction stoichiometric coefficient times the reaction coordinate. Okay? Okay, well, so let me plug in here for N dot 2A. So this is 0.21 N dot air plus minus 6.5 times the reaction coordinate, okay? Times the reaction coordinate. Now the mole flow rate for oxygen, we got the airflow rate for the inlet. That is 185.7. So this is equal to 0.21. 185.7 kilomoles per second minus 6.5, and the reaction coordinate is 3.6 kilomoles per second. And you get an oxygen outflow rate of 15.6 kilomoles per second. 15.6 kilomoles per second. 15.6 kilomoles per second. So that's the outflow rate for the oxygen, O2, in the products. 15.6 kilomoles per second. That's for the oxygen. Remember in the previous example, there was no oxygen in the products. It was stoichiometric combustion. Let's do the CO2. N dot CO2 in the products is equal to N dot CO2 in the reactants plus the stoichiometric coefficient times the reaction coordinate. There is no CO2 in the reactants. And so I get 4 times the reaction coordinate, and I get 4 times 3.6 kilomoles per second, or if you like, what, 15.4? I'm sorry, 14.4. 14.4 kilomoles per second. So N dot for the CO2 in the products is 14.4 kilomoles per second. Let's do the H2O. The outflow product, H2O, is equal to the inlet reactant, H2O, plus the stoichiometric coefficient times the reaction coordinate, epsilon. There is no inflow of H2O, so this is 0. So I have 5 times 3.6. What is that? 18 kilomoles per second. So N dot H2O, 18 kilomoles per second. 18 kilomoles per second. Let's calculate N dot N2. N dot N2 at the outlet, i.e. in the products, is N dot N2 in the inlet, i.e. the reactants, A, plus the stoichiometric coefficient, which is 0, times the reaction coordinate. In other words, so this is 0. In other words, N dot N2 out is equal to, in the products, is equal to N dot N2 in the reactants, which is, by the way, 0.79 N dot air. 0.79 N dot air. I have the airflow rate, so that's 0.79, 185.7 kilomole per second, and I have a nitrogen flow rate of 146.7 kilomoles, 146.7 kilomoles per second. So I have nitrogen, N dot N2, in the products, 146.7 kilomoles. Okay? All right, so let's look at this again. 4 kilomoles per second of fuel flowing into our combustor. Here's the flame. 185.7 kilomoles of air, which is a mixture of nitrogen and oxygen, 21% oxygen, 79% nitrogen. The result is an outflow of 18 kilomoles per second of H2O, 0.4 kilomoles of unburnt fuel, 15.6 kilomoles of O2. So we have not only unburnt fuel, but we have 50% excess air. So there's a lot of oxygen in the products of combustion, the outlet. We have 14.4 kilomoles per second of carbon dioxide. And then we have 146.7 kilomoles per second of nitrogen. Let's write the reaction. Let's write the reaction. And then we shall be done. Let's write the reaction. Let's write the reaction. All right, so we have 4 kilomole per second of C4H10 plus 185.7 kilomole per second times 0.21 O2 plus 0.79 N2 reacts to form 0.4 kilomoles per second of C4H10. That's unburnt fuel. Then I've got 18 kilomoles per second of H2O plus 14.4 kilomole per second of CO2. Yes. Plus 15.4 kilomole per second of O2. And then the last one is a nitrogen, 146.7 of N2. This is our reaction. Reaction. It's not the reaction mechanism. Remember, the reaction mechanism, for this case, only had CO2 and H2O in the products, only had fuel and O2 in the reactants. Everything else, it was for stoichiometric. Everything else canceled out. This includes the effects of the excess air and the incomplete combustion. This is the actual reaction. This is the reaction. All right, ladies and gentlemen, I think that's enough material for 2 lectures here. It's a pretty good start on chemical reactions. What we're going to do next time is we're going to take a situation like this involving some fuel, maybe mixed with air, burned with air, and we're going to apply the energy balance to determine the heat release. So this flame here is releasing a lot of heat. So we're going to apply the energy balance to our reacting systems. What's different about what we've seen up to this point is the intake or the inlet composition chemically is different than the outlet composition chemically. So we've got to be very careful how we evaluate the enthalpies for each component in the mixtures, the inlet mixture and the outlet mixture, the reactant mixture and the product mixture. We got to be very careful how we evaluate these enthalpies. But aside from that, reacting systems are just like any other system. This is just an open system with various mole flow rates of various different kinds of chemicals. There's nothing really special about the energy balance. You're still going to get Q dot minus W dot is equal to dE CV dt plus the sum of N dot H plus on and on and on. We're still going to have the same old thing. It's just we got to be careful how we evaluate properties, because some of the values in the tables there, the tables that you have, the H, the enthalpy values, the specific enthalpy values do not include chemical energy. They do not include the energy associated with the chemistry or the chemical reaction. So we have to be very careful, and we're going to talk about this next time, how we evaluate these enthalpies for these various species or components flowing in and flowing out. Got to be very careful how we evaluate the inlet and outlet species enthalpies. So we'll talk about that next time, and then we'll do a first law or an energy balance problem involving an open system. And then after that, we'll do maybe one more energy balance problem for a slightly different situation. And we'll get some experience involving energy balances on open systems. Okay? Take care, ladies and gentlemen. Take care.